Hello everyone, welcome to CodersArts. So today in this video, we are going to discuss the topic on data structures and algorithms. So as we all know, data structures and algorithms are the core concept of computer science. As you might know, these are the crucial concepts that anyone has to be familiar whenever you are learning any programming language. So be it any programming language, data structures and algorithms are something which make our problem solving skills really simple. So when I talk about programming languages, there may be many kinds of programming languages, right? Like you have Java, Python, C, C++, R, and so many other programming languages. But you know that the core concept of data structures and algorithms has to be applied in problem solving. Especially whenever you're programming, you have to make use of data structures and algorithms. There can be different types of data structures and algorithms which we'll be learning in this particular video. So when I say about data structures and algorithms, firstly, I'd like to give you an introduction to that why exactly data structures and algorithms are used and what is a data structure in the first place. So, data structure is a logical or mathematical model of a particular organization of data. Like we all know, there is data. There is humongous amount of data. So, what is data firstly? Data can be raw data. It's nothing but pieces of information we have. So, such pieces of information have to be stored somewhere. But then, the arrangement of the data has to be done in an organized manner. So, that is taken care of by data structure, which is the logical or mathematical model of a particular organization of data. So, when we have data, be it any type of data. When I say the type of data, it can be an integer data, the numeric data, or it can be string data as well. You might be familiar with the different types of data. Say you have the integer data, which is nothing but the type, it's a numeric type basically, and there are different data types in a programming language. As you might know, int, float is with decimal point or as a floating point number. You can have integers or you can have text as well. So when you are dealing with strings, string data, you get to see text and they have to be enclosed in double quotes or single quotes. The characters have to be enclosed in single quotes and double quotes for the strings. So as you know that the data types are nothing but means to identify the type of data. All the different types of data need some kind of a structural arrangement where they can be stored. So such a storage structure is nothing but data structure. Now we have to, when I say you need this data to be stored somewhere, what is the difference between a storage structure and a data structure? When I say it's a logical or mathematical model for a particular arrangement of data, that is data structure. And the types, examples of data structure can be arrays, linked lists, stacks, queues. You must have heard and you might be already familiar with these terms. But then when I say storage structure, you must understand that there is a thin line of difference between them. So storage structure is the representation of a particular data structure in the memory of a computer. That is termed as a storage structure. So there are many possible storage structures to a particular data structure. Example, there are number of storage structure for a data structure such as array. It is possible for two data structures to be represented by the same storage structure. So when I say this, data structure can be an array or a linked list, but then they can be different storage structures for an array or a different storage structures for the linked list as well. So basically array can be of various types, as you might be knowing, and also you can have different types of linked list. For example, you can have linked list, a singly linked list or a doubly linked list or even a circular arrangement for the linked list. So the arrangement or the structure to represent the particular data structure is nothing but the storage structure. Whereas the data structure is nothing but a logical arrangement of data, we could say. So that is called as the difference between a data structure and a storage structure. And these two terms are different from a database. And that is different concept. Although all of them are storing data somewhere, they are basically organizing the data. But then there is differences between the terms. So let's understand, when we talk about data structure, what are the two different types of data structure? So there are two types of data structures, which are linear data structure and non-linear data structure. This is the classification of the data structure. So under linear data structures, you have subcategories of linear data structures, and under non-linear data structure, you have subcategories of non-linear data structure. A data structure is said to be linear if its elements form a sequence, or in other words, form a linear list. So when I talk about the term linear, as the word signifies, the term linear means it is following basically a particular sequence or a sequential data structure. It's nothing but a linear data structure. But a non-linear data structure, on the other hand, it can have a circular arrangement. It need not be the sequential format, but it can have a circular arrangement or an organization, or it can have a different form of arrangement. Need not be circular. In fact, it can also have a tree-like arrangement or a hierarchical arrangement. For example, you might be familiar with trees again. We'll delve slowly into all the different types of data structures to understand what are trees, the different types of trees like binary search tree, binary tree, and other trees. But then basically they can have different arrangements. So when I say linear, it means the elements form a sequence, or in other words, form a linear list. That is called as a linear data structure. Examples of linear data structure, when we talk about the real life, like let me give you a real life application or real life examples for you to understand linear data structure. So whenever, for example, you are standing in a queue, you're standing in a line, in a counter. So that particular arrangement is nothing but in the form of a queue, we say. So that is a linear data structure because all the elements or the elements in our case over here are the people of a line. So they are nothing but forming a sequential kind of an arrangement. That is nothing but an example of a linear data structure. On the other hand, say for example, you want to arrange the plates of plates. So whenever you are arranging plates or arranging bangles, you have to arrange them, you have to stack them up together. Now when I'm saying the term stack them together, stack is also a data structure. So see, you made use of three different words: array, and I've also made use of queue, and I have given an example of a stack. So stack of plates, or that is also an example of a linear data structure because you're stacking them together, and that is also arranged in the form of a sequence. So whenever now you must be wondering whether it's horizontal sequence or vertical sequence. It can be any sequence. So when I say stack of plates, obviously the plates have to be kept on top of one another. So one after the other on top of them. That is a vertical kind of sequence you're forming. That also is a form of linear data structure. Now, when I say non-linear data structure, then there may be different types of non-linear data structure as well. So, for example, tree, when I already told you, and now what is the application of tree, you must be thinking, right? So whenever you're arranging files of your directory, say in your computer only, you're arranging files, or there are different directories and folders. Inside a particular folder, you have subfolders, and then you have files, and so on. So that is basically it's not a linear arrangement, that is a hierarchical arrangement. Why it's a hierarchical arrangement? Because it's something like inside a bigger folder you have subfolders, and inside subfolders you have multiple again subfolders, and then files. That is nothing but a hierarchical kind of arrangement, because from the top you are then delving deeper. You're delving deeper into the same, basically you're digging deeper. That is an example of non-linear data structure. So, but whereas in linear data structures, you see there is no kind of a division, because it is everything like all the elements are forming a particular sequence and given same kind of priority. So now that you've understood what is the difference between linear and non-linear data structure, let us understand representation in memory. Now there are basically two basic representations in memory. Have a linear relationship between the elements is represented by means of sequential memory locations, that is an array. Now also was talking about linked list, right? Now as the word says, linked list, it is also having the linear relationship between the elements, but they are represented by means of pointer or links. Now say an array is also a linear data structure, and a linked list is also a linear data structure. So when I say linked list, I was also talking about the different types of linked list, right? Like you have a singly linked list, or a doubly linked list, or a circular linked list. They're basically categories of the linked list data structure, which is a linear data structure. But then the key difference comes in the representation of their memory. So whenever there are different elements are nothing but an item, we can say. There's a component of a data structure is called as an element. Now when you have the element basically in the form of an array, so when you have an array, the kind of representation you will be doing is by means of sequential memory locations. That is in the form of for the case of arrays. But when you talk of linked list, all the elements of the linked list will be connected to one another. Like So take, for example, I would like to give you for the linked list is the train. Take the example of a train. You have different compartments of the train, right? And all the different compartments, say compartment number 1, compartment number 2, and so on. They are all linked to each other by some kind of a chain, or there is at least some relationship or association between the different compartments of a train. So that representation is always linear. That linear relationship is represented by means of a pointer or links. So each compartment of the train or the different elements of a linked list are connected to each other by means of links or linked to each other by pointers. So you have to understand this concept, that how exactly we can represent in memory. And you also have to be aware that data structures, because they are nothing but storing data, right? So they have space. They also take up space, they consume space in any kind of programming language. So always our goal should be to optimize the space and use the right data structure that will be more optimal in terms of time complexity and space complexity. Now, what is time and space complexity? We learn about that. Basically, put in simple terms, it means we need to understand that be it any data structure we are applying to a particular problem, we have to choose the type of data structure which will give us a faster operation. Whenever you want to access any particular kind of an element in a data structure or solve a problem, it has to be done faster, isn't it? So you have to basically reduce the time taken by the operations of the particular program. So that is called as time complexity, which has to be reduced. Even the space complexity, which is nothing but too much space. Take any say whenever you're installing any program or a software, the program or software or an app which takes up much space is not considered efficient in terms of space. So efficiency or the performance basically of any program has to be dependent on two major factors, which are time and space, which are the indicators of whether your program is performing properly or not. So when I said what are the types of operations which can be performed on linear data structures? Now we have talked about linear data structures like linked list, arrays, stacks, and queues. We'll be learning about them in detail later, but now I have mentioned these data structures which are linear in nature. What do you think can be done on these data structures? Because see, not all data structures perform allow the same kind of operations to be done. Say, for example, you can do traversal search, insertion, deletion, sorting, and merging on linear data structure. On one other type of a data structure, maybe something could not be possible there, right? Or there is a particular kind of a traversal, like linear traversal, you can do on a linear data structure, but on a non-linear data structure, this cannot be possible. That is, linear search or say linear traversal cannot be done on a non-linear data structure. Over there, you must be have to do the traversal top to bottom, rather than going from left to right or right to left. You must have to be doing it by top to bottom or in a different manner basically. So there will be different algorithms which will come handy, like the depth first search or the breadth first search, which will come into picture when you're talking about non-linear data structures like trees or graphs. So basically operations on the linear data structure are these as listed. Traversal is processing each element in the list. So it's nothing but traversing or encountering each element. You're just processing each element in the list. It can be a list of numbers, basically a data structure which is a linked list. It can store a list of numbers, for example, or a list of strings also. So when be it any element, any type of the element, you have to just process or go one by one in the list. So that is called as traversing. That is the operation you can do. Search is another operation which is finding the location of the element with the given value or the record with the given key. So basically search can be done in numerous ways. So this is a big term here. You might be thinking like search is nothing but finding the index or finding the location of the element with a given value or record with a key. But that is not it. The search can be of multiple types again. They can be a linear search, or you can have something called as the binary search, which is very, very important concept of data structures and algorithms. So binary search is basically more optimal as compared to linear search, because linear search, whenever you traverse, say there is a list and you're traversing the list of n elements, suppose there are n elements and from 1 to n, for example, and traversal time of the time complexity of traversing all those elements will be, or searching all those elements will be, in the worst case, order of n. So when I say order of n, what is order of n? Let us delve into that also. Order is nothing but time complexity basically. So they are determined by the order. So when I say it takes order of n, how to reduce the time to give us a basically less time, so that the time complexity can be improved. That can be done majorly by binary search. So that is a different type of search. So similarly, we can have various kinds of searches, which is nothing but finding the location or the index of the element with a given value. So any element will have a key and a value. See, there is another data structure which is called as a hash map. It will be the hash map is a data structure which consists of key and value pairs. Say, for example, a dictionary. You have a dictionary of words, right? So all the words are in the dictionary. Say a dictionary will have different pages. It will have different words along with their meanings. So the index or the index of the word is something. The index of the word is determined by the key, and the value is nothing but the meaning of the word. That is determined by the value. So that is basically, we can think it of as a dictionary. A hash map can be considered as a dictionary because it consists of key and value pairs. If you might have heard about JSON, that is JavaScript Object Notation, it will be very easy for you to understand what I'm talking about, key and value pairs, because JSON stores the data in key value pairs. So coming to the next operation, which is insertion, it means simply inserting or adding new element to the list. Right? There is a list 1, 2, 3. If you want to add anywhere, see, it need not be you want to add 4 only. It can be even you want to add 6, 7, 8, 9, or be it any number. You just want to add, or it can be a different type of data element altogether. So you're just inserting or appending. You're adding the element to the list at the end, or even in the middle, or even in the start. That is the operation of insertion. Now, there can be different types of insertion we'll be looking into. Then coming to deletion operations, it is removing an element from the list. So when I'm talking about the list, whenever you want to delete an element, say you want to remove the element from different ways, from different places, you want to delete the first element, or you want to make the deletion operation on the last element, or give a particular condition to it and delete from the middle element, or so on. That all can be done. Then next is sorting. See, sorting is again a big concept because there can be different types of sorting. Sorting can be done like insertion sort. To name the types of sorting, let me give you the types of sorting, which is bubble sort, insertion sort, selection sort, merge sort, quick sort, heap sort. The different kinds of sorting algorithms, right? Now, which sorting algorithm we have to use for a particular given problem, that will solely depend on your programming skills, your analytical skills, and how good you are at optimizing the problem by making use of different data structures and algorithms. So sorting is nothing but arranging the elements in some sort of order. Now, it can be the type of the order can be ascending order, that is increasing, or the descending order, that is the decreasing order. You can sort the elements accordingly, and making use of the 5 algorithms which I told you, that is a bubble sort, which is the most common type of sort, insertion sort, selection sort, heap sort, which works on heaps. We look into what is heap also. Heap is basically another data structure, and for heaps we are making use of priority queues, which we'll be discussing in the later stages. And also you have to understand that there is another sort, which is 2 types of important sorts, which is merge sort and quick sort. And these are the most optimal types of sort, because merge sort relies on the and the quick sort. In fact, so merge sort, it relies on the divide and conquer technique. You have to understand what is the different kind of algorithms we are making use for these kind of sorting operations. So next, and also this is what I'm talking about in Java. It can be done in Python also, but there are various, of course, there can be various built-in functions for sorting, for insertion, deletion, and all, like in Python, and for Python, wherever you're making use of pandas, you have something called a sorted, which is already the inbuilt function for sorting the elements. Or talk about in Java, you have the arrays.sort. For example, you have an array of elements and you want to sort the elements present in the array. You use arrays.sort is the function which you use for sorting. That is a built-in function, and all the built-in functions have take not so good time complexity, or not. We can say that they take a moderate kind of time complexity, basically, because it is not too bad or not too good as well, but there's always chances for optimizing. But yeah, if your program is very complicated, and you want to make use of such kinds of built-in functions, definitely you can use built-in functions as they take order of n log n. That is the time complexity. Then coming to merge sort, combining 2 lists into a single list is nothing but merging. Now, you as the name says, it's self-explanatory. Merging is nothing but combining. So combining two lists or appending two lists one or into a single list, that is called as merging. Similar to in pandas, you might be hearing of this function, or in R also, merging two different data frames. There are two different data frames, another data structure in Python. See, I'm generalizing the concepts. I'm not talking in specific to a particular programming language. Definitely we'll be talking more in terms of Java and OOPS, that is object-oriented programming language, but in even the other, which are the non-object oriented programming languages, these kinds of operations will be common to them. So you have to basically understand data structures and algorithms, what is their use. We'll also be looking into the importance of them, then their applications in our day-to-day life, which I've already covered in the introduction and will be delving further. So you have to understand that. So when I'm saying combining two data frames, that is in Python or in R. But when I say in Java, it can be any data structure, right? It can be an array or list. So you can combine two lists into a single list. That is nothing but merging operation. Now that you have understood what is the operations which can be performed on linear structure, let's come to the first linear type of linear data structure, which are called as linear arrays. So array is itself a linear data structure, and let us see what is a linear array. A linear array is a list of finite number of n homogeneous data elements, that is data elements of the same type. So you have to understand the characteristic property of arrays is that arrays is a data structure which is a sequential arrangement of data elements. Now these data elements must be of the same data type. It cannot be possible that if you're making an int array, so that is the way you're initializing the array, right? You're creating an array. So whenever you're defining this array, int array equal to, so the data type of that particular array A has to be some data type, maybe an integer data type. If it's an int data type, then it has to contain all the elements of the integer data type only. It cannot be the case that you are inserting elements of float also, or maybe string in between. That cannot. It is basically containing homogeneous elements. That is, the data type of all the n elements should be homogeneous or should be uniform and same. The elements of the arrays are referenced respectively by an index set consisting of n consecutive numbers. So suppose say you have n consecutive numbers and all the elements in the array are referenced. They are basically, the way in which they can be indexed is done by this index set, and the index always starts that is generally the index value that starts from 0. So always you start the counting from 0 and not from 1. The elements of the arrays are stored respectively in successive memory locations. So there should be a memory location which has to be assigned or allocated to each and every element of an array, right? So that has to be done, and since it is a sequential arrangement, the elements of the arrays are stored in a successive memory location. The number n of elements is called as the length or size of the array. Arrays can be definitely of different sizes, but one important fact is that array data structure is a static data structure in the sense that the size cannot be changed. You cannot change the length or the basically the length or the size of the array. And that is because the data structure array is not dynamic in nature. It is not dynamic type, because if you say list, the size of the list can be increased or decreased accordingly. But when you talk about arrays, say array list is different. It's a different type of linear data structure, and an array is different. So array list is basically a dynamic data structure. The difference between array and an array list is that arrays are having finite size. The size already has to be should be allocated by the user itself before programming. So whenever you're entering a program that is making use of the array, you write it like int a array equal to new int of some value. The size of the value should be provided by while you're initializing the array or creating the array. So the index set consists of the integer 1, 2, so on up to n. Then length or the number of data elements of the array can be obtained from the index set by the length of the array is basically the upper bound minus the lower bound plus 1. Now what is this upper bound minus lower bound plus 1? Upper bound is the largest index, which is called as the upper bound. The smallest index is the lower bound of the arrays. So when you have array of say it's starting from the lower bound of the array is for example, it has to be 0 because it's the smallest index, and the upper bound of the array is 5. So the length of the upper bound, the length of the array is nothing but 5 minus 0 plus 1, which is nothing but 6. So 5 plus 1 is 6. So that is the length. Now length is nothing but, put in simple, the number of elements the array contains. So the array will contain 6 elements in that case. So people get confused that since it's 0 to 5, the number of elements is 5. No, you have to follow this formula, which is UB minus LB plus 1. Element of an array A may be denoted by subscript notation, which is A1, A2, so on up to AN. Parenthesis notation, A of 1, A of 2, and so on up to A of N. Bracket notation, which is A at 1, A at 2, and so on up to A at N. So this is ways in which you can access the different elements of the array. So when I say A at 1, you are accessing the array element present at the first index. Because that is how you are accessing it. Similarly, A at 2 means you are accessing the second element of the array. Or if your index is starting from 0, then you have to do it like A at 0 for accessing the first element. If the index is starting from 1, then this is the case. A at 1, A at 2, and so on up to A at N. Then the number k in A at k is called the subscript or an index, and A at k is called as a subscripted variable. This particular element is nothing but the other name for the element in linear array is called subscripted variables, and the number k, which is nothing but the index basically, which is used for referencing your array. That is called as the number k, is called as a subscript or an index. Representation of linear array in memory. This is how in computer memory you can see basically integer data type, in data type in Java consists of 4 bytes. See, everything in computer memory is stored in bits and bytes, right? So you might be knowing that 1 byte is equal to 8 bits. So similarly, whenever we talk about the data types like int data type, float data type, double, and so on, they have to be considered in terms of number of bytes. So when I say int as a data type of a particular, because int is more common, right? It is an integer data type. So whenever you're creating an array, linear array, having the integer data type or int data type, it consists of 4 as the bytes, because the value of int is nothing but 4 bytes. You have to understand that. Then similarly, 4 bytes is nothing but 4 into 8, which is, since 1 byte is 8 bits, 4 into 8 is 32 bits. Then representation of linear array in memory. Let LA be a linear array in the memory of the computer. So location of LA at K is the address of the element, LA at K of the array, LA. LA is nothing but the name of the linear array. So this is how, representation of this particular linear array is done in the memory location. Now you want to access the location basically. So for that is nothing but the address of the element. Any element. So address is basically the referencing, is a reference value assigned. Whenever you have an element of the array, it has to be determined by some address, right? Or if you have not even an array, but if you say you have a different data structure like a linked list as well. So all the elements of the linked list are connected to each other by pointers. But any linked list element is also consisting of 2 components, and those are the data component. That is the value, basically the data value of the particular element, and the address to the pointing next element. So when I say address, it's nothing but the memory location we are talking about, right? So it is the referencing address of the element. So the element of LA or the linear array are stored in successive memory cells. Since they are stored successively, each of them are connected to the other and they are successive in location. So, in order to remember, the memory is nothing but all about remembering. So the element, every element has to understand and know the address of its succeeding element. Computer does not need to keep track of the address of every element of LA, but need to track only the address of the first element of the array, denoted by base of LA. So the first element of the array is denoted by base of the linear array, and which is nothing but called as the base address of the linear array. So to track any element, you need to keep a track of this base address of the linear array, which is the first, which corresponds to the first element. The representation of linear array in memory. This is how in the memory, by making use of this formula, you can represent any linear array in memory. You can take a note of this formula as well, as it can come handy to you whenever you want to represent the linear array in memory. So location of a linear array at K. K is the index, right? It is a subscript or the index value of the particular element of the array. Then base of LA, which is the first, corresponding to the first element of the array, plus W of K minus LB. W is the number of words per memory cell of the array LA. W is the size of the data type basically. So when you're talking about the int data type, what will be the size of the int data type? That will be 4 because it consists of 4 bytes. So it is the number of words we can say per memory cell or the size of the data type. Then k minus lb. lb is the lower bound you have to, lower bound of the array. So lower bound always in our case starts with 0 if you're starting the counting from 0, or it can be starting from 1 as well. This is an example for you to understand. Find the address for LA at 6. Each element of the array occupy 1 byte. This is how, using this formula, base of LA plus W k minus lower bound. Using this formula, you can see lower bound is 0. As I've told, we are starting the counting from 0 in our case. Then W is the number of words. Then k is 6 because LA at k over here is 6. Each element of the array occupy 1 byte. See, it's already given to us over here that in this particular array, each element of the array occupies 1 byte. So the number of words per cell is nothing but there is 1 byte. So we have to give W as 1 value, then base at LA as 200. Right? So base of LA is nothing but the address of the first cell or the first element of the array. So first element of the array is nothing but starting from the top, which is 200. LA at 0 here. So base of LA is nothing but the reference or the address of the first element LA at 0, and that is 200. So on substituting all these values, you get this 206 as the address for LA at 6. And you can see LA at 6 is the element and the corresponding address of that is 206. This is how in computer memory you can calculate the space. Similarly, following, this is another example in which using the same formula you can calculate. So here we have a different size given, 2 bytes and so on, and corresponding to that you can calculate the address for LA at 15, or be it any element. Basically you can calculate how much what is the address of that particular element. So do note this formula as it can come handy to you. Then once I have explained to you that collection A of data element is said to be indexed is if any element of A called AK can be located, K is a subscript here, can be located and processed in time that is independent of K. So this should always be independent of K. That is the K is nothing but the index. So it is not that the the time, basically it is depending on the K value. It is not that the last elements will be determining the time taken. So they are independent of the K value. Coming to traversing. This is the first data operation I have discussed, which is traversing linear arrays, be it any data structure. So whenever you're traversing, you're accessing and processing each element of the data structure exactly once. You have to exactly once. That is, you cannot, obviously multiple traversals can be done, but for that you have to use maybe for loops, or you have to use some iteration or a recursion concept there, right? But then whenever you're traversing each at least exactly once, that is called as traversing. Traversal operation. See, this is how I'm doing. The cursor over here keeps changing, right? You can see how the traversal has been done. So you can repeat for k equal to lb to ub. That is for the, as I was saying, when you want to repeat, for example. So for repeating this particular traversal, because traversal happens only once, right? It says it exactly once. So when you want to repeat the traversal, you have to use a loop. As I was saying, you can use recursion as well, or you can use iteration. You might be knowing difference between iteration and recursion. Recursion is where you're calling function, basically. You're calling function again and again. That is recursion or repetition. Iteration, on the other hand, is making use of for loops, right? And in terms of space and time, we can say that recursion takes more space. In terms of optimally using space, recursion is using more space. So obviously, to optimize the space, you can make use of dynamic programming and all such concepts, which are optimization techniques to optimize your data structures and algorithms. But yes, definitely you can make use of this for loop as well to iterate over, or to do multiple traversals. So this is a for loop, and you make use of different loops like while loop, do while loop, and so on. Coming to the next operation, which is insertion and deletion. Insertion, as I said, you can add elements anywhere in your particular data structure, beginning, middle, or end. Similarly, deletion can be for removal of an element anywhere in the data structure. Coming to insertion operation, is as the picture is demonstrating, inserting 4 at the end of the array. This is how 4 has been inserted at the index 6. As you have till the 5th index, you have seen that all the elements have been present. But then in order to append or to insert the particular element 4 at the end of the array, this is how you're doing. Then insertion is not possible without loss of data if the array is full. If the array is full, that is a particular kind of programming concept that is called as the stack overflow. So there's basically stack overflow, like basically overflow condition, you can say. If you're talking of a stack, stack is exactly how this is arranged, like on top of the other. You can consider this is stack of elements. For now, you could just take it as array, basically. But then stack is also vertical, on top of another, each other, the elements are placed. So when you're talking of any data structure as such, this overflow is a condition where you have, the particular data structure is full and there is no insertion possible. That is called as an overflow. Now, what is underflow? Underflow is where the index is -1. So there are no elements at all. For example, you have an empty data structure, an empty array without any elements, and you want to delete some element. But then there is underflow, right? Because there is no element already inserted or already present in your data structure at present. So you cannot delete the any element from there. That is called as an underflow. These are two keywords you have to be aware of. Then coming to the insertion algorithm, this is basically, what is an algorithm? This is a word which we have come now. Now I was talking about data structures, isn't it? Now you have to also understand what exactly is algorithm. Algorithm is a series of steps or procedures in order to do a program. So from an algorithm, you get a pseudocode. Pseudocode is something like a small code with the statements, but it's not exactly completely code by applying all the programming concepts or programming logic with the syntax and so on. But it's nothing but in English language only. You are just writing it as you can see here, the steps, basically the series of steps to be followed. You can convert this to a pseudocode, and from that pseudocode, which mainly consists of the main driver function in general, that can be converted to a fully fledged code or a program. So that is how you have to keep. First, your idea should be represented in a flowchart. Flowchart is a diagrammatical representation of all the steps. So all these steps can be converted in the form of a flowchart. Then from the flowchart, you derive the algorithm. From the algorithm, the pseudocode, and then the program. From the program, obviously a program need not be that optimal. You can make, mostly everyone comes with the brute force approach. That is a naive approach to solve any programming problem, right? But then in order to optimize your programming approach, you keep optimizing with the help of different data structures and algorithms, right? You keep on optimizing them. That comes later. So when we talk about this algorithm, which is a series of steps or procedures to solve a problem, insertion algorithm, let us have a look over here. This is the algorithm for that. LA is a linear array with n elements, and K is a positive integer, so that K is less than or equal to n. K is nothing but the index over here, okay? It's an index. Item is the element. N is the size or the total number of elements present in the linear array. Then this algorithm inserts an element item into the kth position in LA. As you can see here, we are initializing the counter. Counter over here is a counter variable. You can make use of I, J, or anything. We're setting it to n by repeating the third and the fourth steps. Now, whenever I say repetition, you have to make use of a for loop here, right? You can make use of a for loop. So move the jth element downward. So this is how you're moving it downward, by basically decreasing. But that is LA at j value, whatever the element is present at this particular location, that will be set to LA at j plus 1th location. So you're moving the jth element downward, basically. That is traversing down in the data structure, right? Isn't it? So then coming to decrease counter, you're decreasing the value j equal to j minus 1. In order to increase, you can do it, set j equal to j plus 1 and so on. Inserting element, this is how you're inserting element. That is nothing but placing your new element. This is your new element to be inserted. You're placing it at this particular index, kth index. So whenever you want to place this new item is a new item you want to insert in this particular data structure LA, which is a linear array having size n and at the kth location. This is how you're going to do it. Just assign the item to LA at K. But that can only be done whenever you are decreasing the count in the first place. So these third and the fourth steps have to be sequentially followed. After you do it and repeat 3 and 4 steps while this particular condition is fulfilled, this is nothing but the counter. And then after this counter is reached, then you come to the 5th step. After the new item is assigned at this particular location, you move on, right? You move on to the next set of elements. So that is done by n equal to n plus 1. You're basically updating the value of n, then exiting it. Exit is nothing but the last step of your algorithm. So this is your insertion algorithm. You can obviously, whenever I'm teaching you now, you can make notes of this so that they come handy to you whenever you are inserting. You want to insert any element into any kind of data structure. This is how you have to be following. and this is for the array by the way. We'll also be looking into insertion algorithm for non-linear data structures like trees, like binary search trees, graphs, and so on. But this is for a linear array, how exactly the insertion of the elements is to be done. Then deletion of the array at the end of the array. This is how exactly, if you want to delete the end of the array, Wagner is present here. You want to delete this particular element, and on deleting or removing the particular element from the 7th index, this is how this can be done. The size of the array gets reduced. As you can see, this is another demonstration example for you to understand your deletion concept. No data item can be deleted from an empty array. This is what exactly I was talking about, the underflow condition. That is, if there are no elements at all, you have the index is -1, then of course there is no deletion that can be done. Similarly, we have the algorithm for the delete. Like I told, for the insertion or algorithm, we have the delete algorithm also. For example, you want to delete this particular item from this list of, or say this linear arrangement of array. You want to delete this item, and you have the n as the value and k as the index of the linear array. Then LA is linear array with n elements and k is a positive integer, so that k is less than or equal to n. Then if you want to delete the kth element, which is item, you want to delete the kth element from the LA, this is the set of series of steps you have to follow. You can make a note of this to understand how the deletion algorithm comes handy in the first place. Okay, so once you have taken note of this deletion algorithm, let's move on to multidimensional array. Multidimensional array, there are 3 types of multidimensional array: 1-dimensional, 2D array, and a 3D array, right? So when we say what is 1D array, example of 1D array is nothing but 1, 2, 3. That is nothing but a 1D array, right? A sequential arrangement, and it's only in one direction. When I say 2-dimensional array, that is an example can be a matrix, right? Because matrix is a 2-dimensional array. And why is it a 2-dimensional array? Because we have rows and columns as well. So when we say a linear 1-dimensional array, 1 cross 1 array basically, need not be 1 cross 1 or 1 cross 3 array also, that is nothing but a 1 row and 3 columns, right? But when I say 2-dimensional array, 2-dimensional array example is a matrix. For example, 2 cross 2 cross 2, or say 2 cross 5, so on. Those are examples of matrix, which is example of a 2D array. So 3D array is another example of an array, right? You can have 3 cross 3. Need not be a square matrix, but it can be another arrangement of matrix as well, where you're having another third dimension added, third direction added to this particular arrangement of your array. This is an example of a 2D array. As you can see, m cross n. But when I say m cross n cross m, or m cross n cross j, or some other element, it becomes a 3-dimensional array. 2-dimensional array, that is a 3-dimensional array has length, width, and height. 2-dimensional array just has length and width, we can say. So this is an example of the 2-dimensional array, and it's a collection of m dot n elements, such that each element is specified by a pair of integers. It can be integer, mostly it's an integer, but of course you can assign any data type to the array. Then the element of A with first subscript j and second subscript k. These are not subscripts, are nothing but the index values. They are denoted by A at j comma k, and that is A at j at k. That is the position. That is the element present in the matrix, or present in the 2-dimensional array at the jth and the kth location. That is, jth is the index of the row, and the column index is denoted by k. 2D arrays. The elements of a 2D array A is shown as below. As you can see here, you have this 2D array, which is of having 3 rows and there are 4 columns. So 3 cross 4 is the size of this 2D array. And why is it 2D array? Because you can see here, rows and the columns are the only the subscripts for accessing any element of the array. So this is how you can represent it. Coming to rows of 2D array, these are rows, horizontal. These are the columns of a 2D array. Column 0, 1, 2, and 3 is represented. Then it is a 2-dimensional array, m cross n. So you can have programming languages will store, array either column by column or row by row. The programming languages which store array, row by row are row major order. That is, row by row arrangement is called as a row major order, and column by column arrangement is called as a column major order. You can have a look at all these programming languages. The more common ones like Java, C++, C, they are the programming languages which store the array row by row, and MATLAB and Fortran store it column by column. Then 2D array in memory. You can see here column major order, like as we have seen the Fortran and MATLAB, they store the elements in this fashion, and the arrangement for row major order is in this way. You can see here row 1, row 2, row 3. This is column by column, whereas this one it's row by row arrangement. This is how 2D array is stored in memory of these kind of programming languages. Coming to the, as we have seen for the 1D array, we have seen how exactly the address of a particular element can be determined. Similarly, for 2D array, whenever we want to find the address of a particular element by accessing, making use of the subscript, this is the formula for it. You can take a note of this formula, base of LA. So everywhere we're making use of the base address. Base address is basically for the first element. For the first element of the 2D array, whatever be the address, that has to be added to our formula in the first place. Then W minus K minus W of K minus 1. This is how you're doing. For the column major order, this is the particular formula. For the row major order, this is the formula. Now, what exactly is J, I and all that? J, so basically K over here, as we have seen, it is the index. So it is the column value, right? Location A at J at K. So J over here is the number of the row, and the column number is denoted by K of A at J comma K, because the first argument is for the row, corresponds to the row, and the second is for the column, before beat any matrix you have, right? So when you want to access any element of matrix or 2D array, this is how you are going to access it. And in the column major order to denote the, or to find out the location or the address of the particular element present in the jth row and kth column, this is the formula. Similarly, for row major order, we have this formula. LB stands for lower bound, which is your starting index. Mostly 0 in our case. So 2D array, row major, this is how exactly we are doing. Kth column, jth row, A at J comma K, right? A at 5 cross 6 is the matrix we are given. This is the formula you have to apply for the 2D row major. Whereas for the column major, this is the formula you have to be using. The kth column and the jth row. Now that you have understood this, this is another 2D array example. So whenever you want to compute the address of A at 12, 3, for example, this element, this is a particular element, and then you want to compute where J value is 12 and K value is 3. Simply by using the formula, you can substitute the values. So on substituting this, you get base of 200, because it's already given in your question that base of 200 is base of A, that is the array, is 200. You are simply substituting base of A with 200. Then W, which is already given in your question, is 2, right? It's the number of words basically. So the size is given as 2 here. N is the size of the array. So when I say 25 cross 4 array, then cross 4, that is the number of columns, has to be considered for the N value, which you are substituting as 4. J over here is 12, because the first argument here, A at 12, 3, that is J. J is 12. LB is the starting index. So when you starting your index with 1, over here we are starting with 1. So you're putting in place of LB, you're writing 1. K, you're substituting with 3. And this is the location or the address of this particular element A at 12, 3, which is 292. Now coming to multi-dimensional array, that is nothing but n-dimensional. Multi-dimensional need not be 3D, right? It can be 4D, 5D, and so on. So that will depend on the n value. That is a multi-dimensional array. As you can see here, of array B is a collection of M1 into M2 and so on up to Mn data elements, in which each element is specified by a list of n integer indices. These are all the different ways in which we can access elements and we can represent them in a multi-dimensional array. Now coming to the concept of the length. How do we calculate firstly the length of a multi-dimensional array? This is similar way as I've told, UB minus LB plus 1. This is common to any kind of an array. The length has to be calculated by upper bound minus lower bound plus 1. Now I wanted to give you also an idea about what is pointer. Now we have talked about array, right? Now you have to also understand the concept of pointer, which comes handy in your C and C++, right? C++ has this pointer concept. In Java and Python, you don't have any pointer concept as such, but for C++ you have pointer. So basically a variable P is called a pointer if P points to an element in data. Data is an array. Okay, so you have a variable P, and that particular variable P in this data array is called as a pointer if it points to an element. So whenever you say a linked list is there, and any element of a linked list will be pointing to or is linked to another element of a linked list sequentially. So that you should link them with the help of pointers in such a way. So you can see here, this is a C++ syntax. So whenever you're declaring pointers, it is this way: int asterisk P, which P is the pointer here, equal to and data at 1. This is a pointer variable p, and this is way in which you can assign the value, that is data at 1. That is the first element of the data array. You can assign it to the p pointer. An array PTR is called a pointer array if each element of PTR is a pointer. So if you have a pointer array, you have to ensure that you have to understand that all the elements of the pointer array are pointers themselves. So if this is a pointer array, PTR at 5, then PTR at 1, PTR at 2, they all are pointers. They are different pointers. And this is the way in which you can basically define pointers in star p and then assign it to a particular value, particular element of the pointer array. That was all about it. I hope I have made this concept of pointers, data structures, linear data structures somewhat clear to you. Coming to the concept of algorithms, I want to first introduce you to data structures, followed by what are different types of algorithms, why we need to firstly make, and why do we exactly need DSA, data structures and algorithms, and the different types of algorithms, what is time complexity, space complexity. Once we understand, then I would like to show you different non-linear data structures as well, like graphs and trees and so on in depth. Now that, and also algorithms associated with graph and tree, we'll be having a look into that. Like as I would mention, I've mentioned you in the starting of the video that DFS and DFS, the algorithms which we use for traversing elements in graph and tree. Let's have a look into that later. So when we talk about algorithms, basically you have to understand few key terms. Now the key terms, when I talked about time and space complexity, this is something to be looked into, because algorithm, the core concept of that is you are leveraging algorithms and data structures to optimize them, to reduce time and space complexity. Now, when I say asymptotic notations are the metric you are following. So this is a way to evaluate or measure your time and space complexity. You need a particular kind of a metric, right? You need a particular kind of a metric or evaluation technique in order to assess the performance of your program. Now, how can you assess the performance of your program? You have to make use of these notations in algorithms. That is the asymptotic notations. Now, the different types of asymptotic notations are big O, little o, omega, theta notations, and so on. It can be big O, little o, then you have big omega, small omega, that is little omega, then you have big theta and small theta. Also, you have to understand the best case, worst case, and the average behaviors. When I say a program is running in the best case, it is where the best behavior is seen whenever the time and the space complexity is the least. That is what is called as the best case. And the worst case is where it is giving us the highest time and the space complexity. That is, it's taking a lot of time and it's not optimal in terms of space, also consuming a lot of space, and an inefficient one basically. Whereas average is something in between, and that is represented by theta notation. These different notations also correspond to different cases. O notation, the big O notation is for the worst case, and the theta notation is for the average, and the small is for the best case. Now you have to identify the differences among all these as well. So let's get started with different algorithms. Basically, what is algorithmic analysis? Firstly, how do we calculate the time calculations whenever you want to see? When I talked about time and the space complexity, there must be a different metric, right? You want to follow a metric, but how exactly can you calculate the time and the space complexity? And in different programming languages also have their own set of asymptotic notations, right? Their own set of basically the time which they are taking. It might run in Java, but the same program logic when you're converting in C++, it will take more time, or vice versa, and so on. So they are basically compiler dependent, we can say, right? They are compiler dependent. So running time calculations has to be calculated. I'll be explaining you that. Then also we'll be explaining you identifying the differences among these three different types of behaviors, and then the complexity analysis. Now, what is algorithms? While I was explaining you in the previous presentation, I was explaining you an algorithm for insertion algorithm, deletion algorithm, right? You can see that they were all the steps of the algorithm. So all these steps of the different program, or the approach how to solve the particular program, they were listed in the steps form. That is 1, 2, 3, 4, right? They were numbered basically. So it's order arrangement. So algorithm definition is a finite set. They're always finite. Now see, each and every term you have to make sure that you understand. When I say finite, that is, algorithm cannot be infinite firstly. It is a finite set of instructions that accomplishes a particular task. Whenever I give you a task or a problem, for example, take the example of making tea. Making tea has a set of steps to follow, right? You have to follow a series of steps for making tea, or preparing any recipe of meal or so on. A recipe also in the numbered form It has to be followed in the form of steps. That is nothing but the algorithm or the procedure, we can say. So that is a finite set of instructions. I hope the definition is clear to you. Then the criteria for algorithm is you should have an input, you should have an output. Whenever I told you to solve a particular task or a problem at hand, you should understand what is the kind of input. Now, while solving any particular problem, you will come across a lot of errors, difficulties and all. So to avoid such errors, you have to understand what are edge cases, basically corner cases, edge cases and all that. All that play a very important role whenever you're dealing with kind of input and output. So firstly, whenever given a problem, the first step you have to identify is what form is the input. That is which data structure you have to use for input. Whether you have to use an array or a linked list or a stack, which data structure will give us a better one to store the input. And whether the input has negative values, does it not allow negative values, so on. These are all the different kinds of edge cases. Whenever you are making any different softwares as well, whenever you're building a different software, these are some of the corner cases you have to always test. So that is nothing but the input has to be tested first. Input, then what kind of output is the program expecting, whether it's in the list form or a dictionary or a different tree form. What is the output, kind of output? Then definiteness, which is nothing but clear and unambiguous. An algorithm obviously can have different variations as well. It need not be one algorithm, but whichever algorithm is concise and also very clear to us. It should not have any ambiguity in it, any confusion in it. That is called as a perfect algorithm. It should be defined, definitive. Then finiteness, it means it should terminate after a finite number of steps. So it should not be running endlessly. It is a finite set of instructions, so it has to be terminated at some point. It also has to be effective. Now, effective means the instruction is basic enough to be carried out. It should be basic firstly. It should also be effective in terms of time and space. How to create programs? So whenever we are analyzing whether program written, a code written is correct, is perfect or not, how can you analyze that? I was talking that whenever you are solving a program, you have to put your problem solving skills and your analytical skills. So when this is where analytical skills come into picture, where you have to identify how to analyze the different programs' performance. So you can do that bottom-up approach or the top-down approach. So design can be done by data objects and operations. You can have different data objects, their operations and so on. Then how to define such programs and apply the coding concepts. To verify the programs, you can perform these three different different types of verification techniques, which are program proving, testing and debugging. Debugging is nothing but solving whenever you have any error, facing any error, how do you basically solve that particular error? You debug it, right? You're solving the particular error by firstly testing it, you program proving it, then these are sequential in nature, like testing it and then debugging it. These are three different types of verification techniques to create programs. So once that is done, you have created the program. Now comes the criteria to check if it is correct or readable or not. When I say readable, this is one core concept of any programming, where you have to understand that it is well documented. Now, documented is where doc strings are added, right? Doc strings are nothing but to make your program more understandable and readable. You need not, so that the software developer team need not always, spend a lot of time to understand the program. If there are doc strings or commented, if there are lines already, there's something like doc strings where they're helping you to understand what each and every step of the code is doing. It is making the program more understandable, easy. That is called as measurement. This is how your program is measured, right? How the performance in such a way by making use of these criteria. Then performance analysis. This is machine independent. You have the space complexity, which is storage, the computing time, which is time complexity, and performance measurement, which is machine dependent again. Machine dependent, whereas performance analysis, which is machine independent. You have to make sure of this. Then program performance. How is it determined? It can be determined experimentally or analytically. So you can either analyze the performance of your program, which is nothing but the amount of computer memory and time needed. As I've already told you, the time and the space are the two major factors which will determine your program performance. That can be done analyzed by you by analyzing your program step by step, or empirically, basically experimentally performing the measure. Then your execution time, in different compilers like Java, C, C++, you might be understanding already, right? How much time it is taken. Down it will be shown whenever you're solving any online compilers, especially whenever you're coding. Down the time taken by that particular program will be given to you, the execution time. Also the space will be given to you, and that space is measured in bytes, kilobytes or megabytes, right? These are some of the criteria for measurement. Then space complexity is defined as the amount of memory a program needs to run an operation. And it is of concern because we could be running on a multi-user system where programs allocated a specific amount of space. So, there are different programs, but then the constraint over here is that the specific amount of space can only be assigned to a particular memory location, right? Basically data structure or to your program. If you do not have sufficient memory on your computer, this is a concern for us. So in such cases, we need to optimize the space or reduce the space. That there are various optimization techniques you can follow, right, for decreasing the space complexity. There are different data structures. For example, a particular problem, in order to optimize the space, you can make use of a different data structure instead of going with one. Or for example, take the example of instead of an array list is giving us a better data structure, because array list is especially more helpful than array because it is dynamic in nature. Array list, the size is not fixed. It can be dynamic or changed accordingly when the user is requiring as per his needs. So that is where dynamic data structure comes handy to optimize the space. To optimize the space, array list can be proven better with an array because array is already allocated a fixed memory space. Such concepts have to be clear to you whenever you are making use of data structures. Then space complexity may define an upper bound on the data that the program can handle. Components of a program space. So there is this program space is basically a combination of instruction space, data space, stack space. You have to understand what these different factors are, like which determine the instruction space, data space, and stack space. Instruction space is basically whatever code logic you're writing. Those will be dependent on these factors, which is the compiler which generates the machine code. Machine code is a common code which is platform independent basically. For example, in Java, we have the Java virtual machine, right? And the Java compiler and the interpreter will do their job, which will convert your high-level programming language into something platform independent, right? You convert into a platform independent language, which is called as a byte code basically, right? So that has to the machine code, then the compiler options that were set at the compilation time and the target computer. These are the factors which will determine the instruction space. Data space is basically related to your data type, not the logic, but your data type. So very much dependent on the computer architecture and compiler again, like you have the data type like char, short, int, long, float, and so on. So you can make use of this. The size or the space of this data type is given by the data space. Then coming to the small, you can use a smaller data type in order to optimize your space, but it again depends on your problem you're solving. Then coming to the environment stack space, it is the following, which is following data saved on the stack, which is the return address. The address is one such important point you have to understand, which is a core part of the stack space. Then the values of all the local variables and the value formal parameters, then the binding of all the reference and the constant reference parameters, these all come under the stack space, which impact the environment stack space. Now that you have understood complex, space complexity, you must be hearing that there are different algorithms like, recursive algorithms, then there will be iterative algorithms, dynamic programming, and so on. The sole purpose of any optimization algorithm is to reduce your space and time complexity. As you can see, this is an example for you to understand how to calculate space complexity. So this is a particular variable, you're assigning a space. So you're assigning 0.0. This is 0.0 is of which data type? It's a float data type, right? 0 is an integer data type. So whenever you're assigning this particular to s, then for I equal to 1 to n, you're running a for loop. So since you're running it till n, you know that till n, it is nothing but n times it is running 1 to n. So order of n basically. So you're performing this operation, s is equal to s plus a at I. You're basically adding this particular value of the variable to s variable and then returning s. Now, how much time do you think each step will take? This will take 1 is the space, then this is going till 1 to n and so on. So when you see here, space needed to store n equal to 1 word, then space needed to store a at n equal to n floating point is n words, because the loop starts from 1 to n, it will take n words. Then space needed to store I and s is equal to 2 words, right? To store I variable and the s variable, that will take 2. So hence totally it will be s of p, that is the space of the program would be n plus 3. So now that you have understood what is the space complexity, now what is this time complexity, how is it measured? It is basically count a particular operation counts is done, then counting the number of steps, which is the step counts which has to be done, then asymptotic complexity. You have to, by these three metrics, you can understand and compute your time complexity. And it is the amount of computer time a program needs to run. Now let's quickly understand how time complexity can be calculated. Let me explain you with an example so that you can understand it better. So for example, each statement will be taking some amount of time. This particular statement, if you see it, this is the thing, nothing but the method definition. This is how a method is defined. It's taking 0 as a time, 0 seconds, or so if you see s is equal to 0, this is taking 1 as a total time, I equal to 1 to n. Since it is iterating or repeating till n, it is going to take n plus 1 as a total. It's the frequency. Frequency is the number of times it is repeating or number of times it is occurring. So this will take n plus 1 as a total time. So s is equal to s plus a at I. S plus a at I, this would take n times, because whatever is inside your for loop, that will, you have to understand that whatever is inside your for loop will take n as the number of time, basically the number of steps counted. But then whatever is here, your basically first line of your for loop statement, or be it any iterative statement, that will take n plus 1. Okay, you have to understand this. This will take n plus 1, but whatever is inside your for loop, the body of the for loop will take n. Okay. So whenever you are repeating from I to n, then return s. This is just one line. So it is, in fact, it is outside your for loop. It is not inside your for loop. Had it been inside your for loop, it will take n. But it's outside your for loop, so it will take 1 only. Just add all the time taken for each of the step or each of the statements, and you will see that the time will be 2n plus 3. Now that you have understood how the time complexity is calculated step by step, all this, now basically time complexity of a program, you can say, is cumulative in nature, right? Your cumulative means you're adding all this individual time complexities, or adding the individual time taken for each executing each statement. That will give you the total time taken for the program. So in this case, if you see, similarly, you're calculating the here. Let me just explain you why. This is taking 0 as a time, because nothing is just the method definition. This is nothing with the braces, again 0 time. Now see, this is the first line of the for loop, and I told you first line of the for loop takes n plus 1, but the body of the for loop will take n, right? But there is another nested for loop here, right? There are two for loops here, basically. One which is nested or enclosed inside another outer for loop. This is nothing but n into m plus 1, because this particular for loop will take m plus 1, but then whatever is inside this outer for loop, n, that is executing n times, that has to be multiplied with m plus 1. So n into m plus 1 is done here, then followed by whatever is inside this inner for loop. This takes m, but then it's also inside this outer for loop which takes n, right? I told you whatever is inside the outer for loop will take n as a time, whatever is inside the inner for loop will take m as a time. So you're multiplying n into m. Then this single statement which is outside this entire outer for loop and the inner for loop, this statement is outside, is just a single line, so it's taking 1 as the value. The total summation of all these individual time steps or the counts is nothing but 2nm plus 2n plus 2, which is the total time complexity of this particular program. Now coming to the running example of the insertion sort, this is the, I've shown you the algorithm for the insertion sort, isn't it? Now this is the program. The same algorithm can be converted in the form of a program where you're making use of this for loop here. And for loop is starting with the counter variable. This is the conditional statement. The second part is the condition statement. First is the initialization statement. Finally, the last is the updation statement. Updation statement is nothing but increment or a decrement. It can be an increment operation or decrement operation. Since we are performing insertion, it is an increment operation here. So as you can see here, these are the series of steps you're performing inside this particular logic, inside this insertion sort. You can also make a note of this insertion sort algorithm, so that whenever you're inserting any values into an array, these are the steps you have to follow. This is the code for that. Then operation count, comparison. This is another, now let's understand what is operation count. Operation count is nothing but determining count as a function of this instant characteristic. Now what is this instant characteristic? N is the number of elements in case of insertion sort, right? Now how do you determine the count as a function of this insertion characteristic N? That is nothing but the number of comparisons. So whenever you are making the counting, the not the number of steps as we have seen, but counting the number of comparisons we have, which have to be done, that is the operation count. Because the operation done here is the comparison operation. So whenever the number of comparisons to be done is nothing but the operation count. The number of compares depend on the A's, the arrays, and T as well as on N. These are the determining factors, basically T, N, and arrays. So worst case will give the maximum count, best case count will be nothing but the minimum count, average is the between the worst and the best. Now that you have understood the different types of the operation count, let us understand what is a worst case operation count, right? Worst case is where it is giving us the maximum number of comparisons. We have to perform maximum number of steps in order to solve our problem or to solve our logic. That is called as worst case. The simple thing, the same thing, same kind of logic can be done simple in one single line of comparison or one single compare. In that case, that is called as the best case, because we are not performing much work, or we are not performing much number of operations to reach a particular target. That is called as the best case. But for the worst case operation count, we are performing number of operations. So if you see here, 4 is the number of compares. If I say that in another program logic, the same can be done in just 2 compares, then we can say that is more optimal, right? We are just comparing less number of operations. We are performing less number of operations. In this case, we are performing more number of operations. So that is called as a worst case. So the total compares over here is nothing but, as you see here, this will take n plus 1. The first line of this will take n plus 1. This is inside the for loop. This will take n times, right? And if you are summing up all the total number of compares, it will be from 1 to n minus 1. And you know the summation of all the elements from 1 to n minus 1 is n minus 1 to n by 2. This is a mathematical formula, as you might know, for the summation of numbers from 1 to n. 1 to n, it is n into n plus 1 by 2. But over here, it is n minus 1 to n by 2 because it is ending till n minus 1. Now that you have understood what is operation count, step count similarly can be done. Operation count was the number of comparisons we are counting. But in step count, it omits accounting for the time spent on all but the chosen operation. Step count is for each step basically of the program. It is not for the entire operations, comparisons of the whole program, but it is for each step of the program basically. That is called as a step count, and for the chosen operation you have. It is not counting for all the operations, but for this chosen operation. So as you see here, the steps execution over here, it is clearly mentioned to you. This will take 1 as a step, 1 step per execution. Then similarly, you have 0 over here because just the brace here. Then 0 over here because it's a comment. This is a comment. Okay, in Java you use this as a comment. In Python you use, instead of this 2 backslashes, you use the hashtag, right? Similarly, you can comment in different ways. Then this will take 1 and so on. Adding all this will give you the summation, total step count of the program. So frequency is given in this way. This is the step count. The frequency is n minus 1 and so on. As I've already explained you how exactly for the inner for loop, outer for loop, the body of the for loop, the counting has to be done. Once you have calculated the frequency of the number of times it is repeating, the sum of all that, the total when you were doing the summation for the entire program, it can be in any order. Before I was explaining you with a linear order, that is n plus 4 or something like that, right? But it can be so happening that it can, whenever you're multiplying n into n, it will give us a square value, n square. So over here we can say the degree of the program is 2 here. Degree is the, in maths you might be knowing that degree is the highest order or the highest power, right? So the highest power of all the variables present here is 2. So we can say the degree of the program is 2. Or we can simply say order of n square. It is of the order n square because n square is the most significant term here. The 4 can be neglected here. It's a negligible term. Does not, it is very less small compared to the bigger term n square. So the most significant term can be termed as order of n square here. So asymptotic time complexity over here is nothing but it provides us meaningful statements about the time and space complexities of the program. That is why we are making use of asymptotic complexity. When I was saying you that big theta and big O notation, small O notation, theta notation, and so on, these are different asymptotic notations you're using, order of, so on, and that is basically for you to understand, predict the growth and runtime, to compare the time complexities also. When I want to compare their 2 programs and you want to make comparisons of the time complexity of 2 programs that compute the same function, you can make use of this asymptotic complexity. It provides meaningful statements about the time and space complexities of the program. Then you have this complexity example as well, where 2 programs have complexities so and so, and then how do you exactly, compute and compare the performance of the complexity of the 2 programs. So that can be done by making use of asymptotic notations. Then, as you can see here, you have to basically understand whenever you are talking about asymptotic notation, it describes the behavior of the time or space complexity for large instance characteristics. So big O notation provides an upper bound, as it says, it's the upper bound. Omega notation is for the lower bound. Theta notation is used when an algorithm can be bounded both from upper and below by the same function. So between the upper bound and the lower bound, the notation is the theta bound, which is for the, expressing it. It is for the algorithm which can be bounded between the big O and the omega notation. Then the little o notation, which defines a loose upper bound. It is also a small, so you can see it's a O notation only, right? It's a O notation, but it is an upper bound, but it is a loose upper bound because it's still little o. But big O on the other hand, it is a tight upper bound. This one is a loose upper bound. Little o is a loose upper bound. These are different ways in which we can bound our program. Now, what is this bounding exactly? You remember when I was talking about the length of the array or the data structure, I was talking about upper bound and lower bound there as well, right? Upper bound is a higher value, lower bound is a lower value. So whenever you are concising, whenever you are putting it into a particular range of values, followed by the upper value, higher value, which is the upper bound, lower value, which is the lower bound. That is for basically concising or basically putting a kind of constraint on your program, a range of your time. It can be space for your particular algorithm. That is for measuring your the growth of your program, and to compare them, you're making use of these kinds of notations, right? So once that you have understood this, what is this upper bound and so on, upper bound comes handy with the worst case. So basically T of n, when I'm saying it is a function of the problem size n. So to calculate the time complexity, the running time of the program in the worst case, that is the number of steps it requires at most, the maximum number of steps the program will take to complete a given task, that is called as the worst case. The mean number or the average number of steps required to complete a large number of with a large number of random inputs, that is called as the average case. So when I say the sorting algorithms, right, I was explaining you the different 5 types of sorting algorithms: bubble sort, insertion sort, the selection sort, heap sort, merge sort, quick sort. So bubble sort is the most common one, but although it's the most easy, it is not that effective. You know, in most of the cases, bubble sort will fail because it's making comparisons on side-by-side elements. That is, comparing each element with its adjacent element. But that is not always efficient. Why it is not efficient? Because it is having a higher worst case. That is, it will take a lot of time basically. The time complexity taken by the upper bound, basically the bubble sort algorithm, is more. So it is not optimal. So we can say that for sorting a given problem, the worst case will be done, for example, in bubble sort, right? But then similarly, the best case can be achieved by a different algorithm, say a different algorithm like merge sort or quick sort. So that is for the best case. For the worst case, it is bubble sort and so on. So it is the time complexity of this value. So it is not necessary to know the exact value of T of n, but only an upper bound as an estimate. So when you know the upper bound, we can say that we know the worst case. We know the worst case of the algorithm. That is how you can calculate, you can compare basically the worst case, average case, and the best case. Then for the bubble sort, generally it is order of n square. It takes n square amount of time, and that is not optimal because, you know, for time complexity, the least you can get is order of 1. That is for the best case. Then simply sometimes instead of order of 1 is something called constant time and space. It is not actually ideally possible that all the complex programs and making softwares, it will take order of 1. So they definitely take order of n. So order of n can be considered up to order of n, that can be considered optimal. Then you have n log n, right? And in between 1 and n, you have log n. Log of n is obviously less than n, right? Logarithmic of any n value is less than the n value. Log of 2 is less than 2. So we can say log n is also a better, is a good time complexity or space complexity. We can say a good measure for the program. Then similarly, as you keep increasing the time and the space complexity, you get the bigger terms like n square, n cube, n power n, 2 power n, and so on. All that comes handy when you're using, dynamic programming. So in order to optimize such huge amounts of spaces, especially while dealing with recursion trees and all that, you have to optimize them. So over there, you will see 2 power n, or order of, n cube, n square, and so on coming into picture. So now that you have understood this, big O notation is something like this. It is the definition of big O notation is this one. In general, the order of the asymptotic notation can be of this linear, quadratic, exponential. As I've told you, that is order. Similarly to maths, in mathematics, you might be studying about the order, the highest power basically of the degree of the variable. That is called as order. So whenever I'm saying the definition, f of n is a function, it is order of g of n. It can be expressed in this way. This is for the big O notation. And you can just make a note of this definition. This is the exact definition of the big O notation here. And what is this O of g? O of g comprises of all functions f for which there exists a constant c and a number n naught, such that f of n is smaller or equal to c into g of n for all n comma n greater than or equal to n naught. N naught is the initial value basically. It's the smallest value for your algorithm. nothing but a constant only. Small, you can take the constant by trial and error. Whenever you'll be solving the asymptotic notation problem, you'll be coming across as n naught and c. These are nothing but constants, but these constants can be defined by the user itself, by the programmer. So you have to set the constant in such a way so that you get the least worst case, the less time. So in this is the notation for big O, that is f of n is equal to O of g of n. You can make a note of this big O notation. Examples of big O notation, as I've told, in bubble sort, it takes order of n square, right? So similarly, order of n square is the complexity class of all the functions that grow at most quadratically. It's a quadratic notation. Similarly, for linear, you have order of n. For constant, you have order of 1, which is especially the best case. Then order of n power k, you can have n, k can be anything, right? It can be n square, n cube, n power n, and so on. These are polynomial functions. Lower bounds. Lower bound is nothing but it is opposite of your upper bound, where a certain number of steps that every algorithm has to execute at least in order to provide the problem, to solve the problem. So in upper bound, we have seen the number of steps that the algorithm has to execute at most. That is the maximum at most. But then in the lower bound, it is the minimum number of steps the the algorithm has to take in order to execute. So it is the least number of steps at least to solve the problem. That is called as a lower bound. So for sorting, we can, for example, when I was talking about the sorting, the least number of steps you can contain is n. So we can say it's a linear sort, order of n. So n we can say is a lower bound for our sorting problem. But to sort a particular group of elements, the highest number of steps it will take, the maximum number of steps it can take is order of n square. That can happen in the case of bubble sort, right? So these are the different ways in which upper bound, lower bound can be deciphered. Then we have the omega notation for the lower bound. This is the definition of omega notation. Please take a note of the omega notation because this is exactly the definition you have to understand. See, this covers everything basically, because if you're representing f of n as a function as omega of g of n, which is read as omega of g of n, if and only if positive constants c and n naught, these are positive constants such that, now how you can choose these two positive constants and this function is such that f of n is greater than or equal to c into g of n for all n comma n greater than or equal to n naught. You have to understand this omega notation. This is the way in which we can define our omega notation. Once that you have taken note of this omega notation, these are some of the examples for you to understand. So when I say omega notation for this particular program, you have this f of n as an example, and then g of n is this notation. So since c equal to 1, c is a constant here, and n naught given as 2 here. So we have to understand that this particular value, since we had this particular equation, f of n is greater than or equal to c into g of n, we have to apply this for solving this omega example. This f of n greater than or equal to c into g of n. G of n is n square here. Then on solving this is nothing but the omega notation. F of n is omega of g, this one. So you can see here in this example, it lies in omega of n square as well in order of n square. It grows at least quadratically because the degree over here of n is 2. So we can say it's a quadratic notation. So it grows at least quadratically, but also at most quadratic. At least is nothing but, at least is indicating omega, at most is indicating order, right? Big O. Big O of n square is at most, at least is omega of n square. This is different ways in which we can represent the omega notation. Now coming to the theta notation. Finally, theta notation is for the it's for the average case. So whenever you are talking about the average case, that is a theta case, and most whenever it's talking about n square and n square, for example, is for the worst case. Then for the best case, you have n as the time taken. So between n square and n, you have a value n into log n. That is where the theta comes into picture, because it's mostly for the average case. Now, for example, it is possible to sort faster. Instead of n square, which is for the bubble sort, there is an optimal way to solve the sorting problem. The problem we have at sorting, right? We have a sorting problem at hand. So when we say to solve the same problem faster, we can solve the same problem in n log n time. And n log n is the time complexity of a particular sort, which is called as a heap sort algorithm. Okay, heap sort. Now, what is this heap sort? It is an optimal sorting problem since its upper bound matches the lower bound for the sorting problem. So it's an optimal sorting problem. This is the theta example. Similarly, we have the little o notation. You can take the definition of the little o notation, which is a loose upper bound. Simply just remember it's called as a loose upper bound. And this is the hierarchy of growth for the rate functions. The functions which take only one or the constant time are the best. and this is the worst case, which is for the n power n. If the function is taking like, polynomial notation over here, n power n time or the space, that is not considered efficient. So on the left hand side over here, starting from 1, it is the best case. This is the worst case. In between, you can have any number, any time. You can have the any value for the order to measure the space of the time complexity. So over here, this is the order. 1 is less than log n. So 1 is considered best, right? Then you have log n, which is less than, or log n is less than n, is less than n log n square, n cube, and so on. So ideally, we can say that up to n, it's considered as your program is giving you a good time and space complexity. If it goes n log n also, like in heap sort, as we have seen, that is also considered good in some cases where there are, complexities arising. N square, yes, definitely, whenever you're talking about the deep, this dynamic programming and your recursion, then n square is fine, but n cube is not considered optimal. So whenever you are solving any comparative programming, it is always ideal for you to, try to limit your time constraint, your space in your time complexity up to n log n, or at most till n square. If it exceeds like n cube, 2 power n, these compilers and the, all your comparative programming compilers, they would not accept these kind of time complexity and space complexity values for your output. So these are not considered as efficient. But then definitely when you have a lot of data and space available in real life as well, it might go, the time complexity might be this much also, but in scientific applications as such. But then, it's this is the hierarchy in which you have to follow. So always it's better to optimize your time and space complexity. Make a note of this hierarchy of growth functions as well. Then this is a quick recap for you, where this is called, 1 is called as a constant, log n is the logarithmic value, n for the linear, n log n quadratic for the, because the order or the typically these are also mentioned over here, that for what kind of applications or what kind of case scenarios you will be getting these kind of time and the space complexities. You can see when the growth is independent of the problem size, it is not depending on the size of the problem, then it takes constant. If it is, linearly growing to the problem size, like in binary search is very important type of algorithm you have to understand, because when I say that a linear search is taking order of n, right? It's taking order of n. For example, you want to traverse a list of elements. It takes mostly the linear time, order of n. But then similarly, when you apply binary search, it will reduce your time complexity and it will just give you log n time. So we can say binary search is more optimal than linear search for traversing elements. Yes, then you get n log n, which is typical of some divide and conquer approaches. So in merge sort, when you take, when I was talking about the sorting algorithms, the bubble sort will take quadratic time. It will take order of n square. But if you apply merge sort, quick sort, it will just take order of n log n. So that is more optimal. So this is the way. You can just make a note of where, in what cases you will get which time complexities. This will be helpful for you in solving, answering different interviews. Then quadratic, typically nested loops, when you have a loop nested inside another loop. Cubic for more nested loops, and exponential where it is, growth is extremely rapid and possibly impractical. This is an impractical case, 2 power n, because it is not usually recommended and it's not an ideal case as well. So these are the practical complexities. You can have a look over here. N log n, n square, different ways in which the overly complex programs may not be practical given the computing power of the system. So if this is computing power, complex programs, they may not be practical, like 2 power n, exponential growth. This is something which has to be ruled out, right? So these are some of the possible cases in which the complexities may arise. Now that you have understood that how the algorithms are taking up space, how exactly you are making use of different data structures and algorithms, and I've also understood the classification of data structures and algorithms. In the next video of ours, in the upcoming video, I would like to explain deeper into the non-linear data structures, where I'll be discussing giving you a nutshell about different, the different data structures, linear data structures. We have already discussed. We'll be delving deeper into them, like stacks, queues. For now, we have understood everything about arrays and linked lists, right? I'll be delving more deeper into linked list, stacks, queues, the linear data structures. Then also we'll be explaining you the non-linear data structure with special reference to binary search tree, binary tree, and also we'll be explaining you the graphs and the algorithms associated with graphs, the different types of graphs, something about the graph theory, because graphs are a very important concept that you have to master. Whenever you are talking about data structures and algorithms, you have to come across this concept of graphs. So I'll be explaining that in the upcoming videos. So have a good day, and if you have any doubts, please feel free to drop in your comments box. Thank you. Hope you liked the video.